Cool. All right. Um, let's get started. This is gonna be a jam-packed talk. I'm very stoked. So my name is Joey, and today's talk is about making the gadgets that we make last longer. Some of y'all might know me from Sensor Watch, the low-power board swap for an old Casio. I am wearing 4 of them right now. I actually started one of these on a fresh battery today, and it's interesting that this is coming right after Carrie's talk because it is a battery like this, a coin cell. This is a CR 2016 coin cell, and I'm going to zoom in on the top here. We can see its rated capacity, 100 milliampere hours. So to help give you an intuition for this kind of energy, I will compare it to the battery in another gadget, the iPhone 16e. So this iPhone has a battery capacity of about 4,000 milliampere hours, which looks something like this, 40 of these coin cells. Still, with this impressive battery, it doesn't actually last that long. Like, this thing only lasts a couple of days. If you own one of these, you probably recharge it every night. By contrast, I once wore a sensor watch with one of these coin cells for 873 days without recharging at all. We managed to stretch that 100 milliampere hour capacity to nearly 2.5 years by focusing deeply on power consumption. So that's what today's talk is all about. Optimizing your choices when making hardware and writing software to squeeze the maximum amount of life from the minimum amount of juice. So I'll preface this by saying you can't optimize what you can't measure. This is pretty obvious. So we're going to need some kit to measure our power consumption. But luckily, there's a good piece of kit available, this Nordic Power Profiler. It's just $100. I love this thing. I'm going to show a bunch of power traces throughout this talk. And all of these are power traces that I generated using the Power Profiler. You plug it into USB, it can feed your gadgets 5 volts, and it can measure how much current that gadget is drawing. Okay. So I figured we'd start by power profiling a really common dev board, Adafruit's Circuit Playground Express. I love this board. I use it in classes. It's got a SAM-D21 microcontroller up top and a whole bunch of useful stuff. So to get a sense for how much power this board consumes, I figured I'd load up everybody's favorite program, Blink. You have seen this program before if you've ever opened Arduino. Very simple, configures an LED as an output, and then blinks the LED on and off, 1 second each. So this is my setup for profiling the board. I have the Power Profiler's output plugged into the board's battery input. And I'm going to feed the Circuit Playground board 4.2 volts, the nominal voltage for a LiPo battery. The resulting power trace looks something like this. We're seeing 10 seconds of time on the x-axis and the amount of current drawn on the y-axis. So it's pretty easy to see what's going on here. When the LED is on, the board is drawing maybe about 23 milliamperes. And when the LED is off, the board is drawing about 21. We can also see at the bottom left here an average. On average, over the course of 10 seconds, the board is drawing about 22 milliamperes of power, of current, rather. So I'll be the first to admit, Blink is kind of a contrived example, but we are here, so let's go ahead and try to optimize our Blink sketch. We're going to try 3 main strategies here. First, obviously, we can strategize about ways to bring the entire line down. Like, we're averaging 22 milliamps, but if we can figure out some way to optimize our overall power consumption, we can move that entire line down. We can also try to focus on the parts of the trace where the power consumption is lower. Like, if the LED is off, we can try to optimize the situation where the LED is off to bring the low parts of the line down. We can also try to attack the most power-hungry parts of our code, the part where the line is high. Like, the LED is on, it's drawing power, but we don't have to be wasteful. We can try to find the parts of our code that are doing too much and put them on a diet. So first, in terms of bringing the whole line down, we can eliminate unnecessary stuff. One of the reasons I like the Circuit Playground board so much is also one of the reasons it doesn't make the best choices for our Blink sketch. It has all this extra stuff. It's got a light sensor, motion sensor, all of these extra like NeoPixel LEDs outside. Each of those can consume up to 1 milliampere of power, even when they're not lit up. So yeah, if you were designing your own board for Blink, you could choose not to put some of this stuff on it. Or, in our case, we can just choose a different dev board for our purposes. This Feather M0 has the same SAMD21 chip in the middle, but there's really not that much else on it besides our red LED. So by choosing a different dev board here with less stuff, we've moved our line from up here, 22 milliamperes, down to here, just 12. We've nearly cut our current consumption in half. Okay, for the next piece, we can attack the low parts of the trace by trying some sleep modes. So show of hands, who here has used Adafruit's Sleepy Dog library? Cool, I see a few hands popping up. Right on. We're going to talk more about sleep modes in a moment, but for now, let's just say I can take my delay line out, and I can replace it with this lower power version of this, which still times 1,000 milliseconds. This command puts the CPU to sleep while it waits that 1,000 milliseconds. So with the CPU asleep during the low parts of our trace, we've moved that part of the line from here down to here. We are now averaging just 6.4 milliamperes. All right, so now we can try to attack the high parts of the line. And the good news here is we can actually use that same strategy. Because we do need to use the CPU to turn the LED on and off, but it doesn't have to be waiting around, sitting there consuming power when we're just waiting 1,000 milliseconds. So by replacing that delay line with our same low power sleep function, we can bring the high parts of our line from up here down to here. Now we're consuming just 612 microamperes. That's less than a milliampere. Yeah, we've come a long way just by changing 2 lines of code. And it gets better if we can modify the hardware. So if you're designing your own things, you can try to select components that are more efficient. All right. So this bit, I admit, is a bit in the weeds for the first beginning of the talk, but bear with me for 30 seconds. These are graphs from a datasheet for a red LED, like the one in our Feather, as well as a high-efficiency green LED. So on the left, they have very sort of different responses to forward voltage. But on the right, in terms of forward current, it's pretty linear. The more current we feed to the LED, the brighter it's going to be. And these brightnesses are relative to their brightest point. So at 20 milliamperes, the red LED gives me 0.68 lumens of light. Whereas at that same 20 milliamperes, I get 1.9 lumens of light from the green LED. So this is one way to look at it. I can get more light for the same amount of current. But another way to look at it is, if I only need a half a lumen of light, I can buy that for one price with the red LED, 12 milliamperes, but I can get that for a lot cheaper with the green LED, just 4.5. So I've soldered this much more efficient green LED at the bottom right. With this new, more efficient LED, my current consumption has moved from up here down to here. We are now averaging just 387 microamperes of current consumption, which is a big improvement just 8 minutes into our talk. So to give you an idea of the real-world impact of this optimization, let's compare where we started to where we ended up. Let's plug this board into a battery, say this 400 milliampere hour battery that's designed to fit underneath our Feather. The original Blink sketch consumed 21.65 milliamperes, which is 21,650 microamperes. Our improved version consumes just 376. This is napkin math, I admit, but if we naively divide the capacity of our battery by our current consumption, we end up with 18 hours of blinking for the sketch on the left, and 44 days of blinking for the sketch on the right. Now, this is napkin math. We might be off a little bit, but the point here is you can improve the power budget of your gadgets by literal orders of magnitude. What's required is to have a low power mindset. And to that end, I have structured today's talk as 5 lessons in low power thinking. So let's get right to it. Lesson 1. I titled some of these kind of funny. I called this one Brain, Brain, Go Away. But really, it's just a more detailed look into this CPU sleep thing. So if you ever look up the electrical characteristics of a microcontroller's in a microcontroller's datasheet, you'll almost certainly find a table like this. This is from the datasheet for a microcontroller that we're going to be playing with in just a bit. and it's listing the current consumption in milliamperes for the chip doing a variety of tasks. But if you scroll down in that table, you'll likely notice some entries like this. This part of the table is showing power consumption in standby mode, and these numbers are a lot lower. They're lower because they're in single digits, but they're also lower because look at that unit, microamperes. Like, if you take nothing else away from this talk than this, let it be these orders of magnitude. Like, drawing 4 milliamperes doesn't seem like that big of a deal until you realize that drawing 4 microamperes could be so much more civilized. Like, that 4 milliamperes is 4,000 microamperes, which feels positively gluttonous once you realize that single digits are possible. So how do we get there? Well, I like to start by thinking about, let's get rid of the thinky part. Even in a microcontroller-oriented project, the CPU inside there is probably the biggest pile of transistors involved, and they're all switching on and off, doing thinky things whenever the CPU is running. If we can turn the CPU off, like we did with this watchdog.sleep line, we can get rid of most of that switching, which accounts for a lot of the power consumption in our gadgets. So behind the scenes, Adafruit's Sleepy Dog library put the CPU to sleep and woke it back up after 1,000 milliseconds. Now, I can hear you saying, that's fine, Joey, I get it, but I aspire to more than a blinking LED. So for this next exercise, I'm going to light a candle. And I'll put up on screen what I'm actually lighting up here. I designed this little candle as an example for a class that I taught this past semester. And the premise of it is it's an electronic candle, but we're going to light it with a literal flame. Okay. So this is the schematic for our candle. It's powered by a relatively simple microcontroller, the SAMD11, and it has 2 sensors in it. It has a photoresistor that can sense the light from my flame, and it has a thermistor that can detect the heat. But I will say, I designed this board with a couple of flaws, mainly so my students could explore those flaws through the lens of a question. How long will our candle burn? So to figure this out, we're going to need 2 numbers, the capacity of our battery and the current draw of the gadget. Once we have those things, we can napkin math our way to an estimated runtime for this thing. So let's do capacity first, and there's an important point here. The battery in this candle is smaller. I'll turn it around so you can see. It's just physically smaller than the one in Sensor Watch. The 2016 had a diameter of 20 millimeters. The 1220 has a diameter of 12. And that's just because it was the only way to make it fit into this svelte candlestick profile. Pulling up the datasheet for the CR1220, we can see that it has a typical capacity of just 37 milliampere hours. So less, like maybe a third less, or 2/3 less. It's less. So that's one term down. We now have the capacity of our battery. What about the current draw of the gadget? Well, this one's going to be tougher because the candle has 2 modes. It had one mode where it was dark before I lit it, and it has another mode now that it's burning bright. So the answer to this question is going to depend on code. So let's write some code. First, I'm just going to assume that we have 2 functions that can turn the candle on and advance the frame. So now let's write our main function. We're going to configure the temperature sensor as an input to an analog to digital converter and enable that converter. We're going to set that up. Now we can get into our main loop. We're going to sample the current temperature value from the ADC, and if it's above a certain threshold, we know that someone has held a flame to the candle, and it's time to turn the candle on. Then we're going to enter this inner loop, where we just advance the animation frame, delay, and we're just going to burn the candle like this until the battery dies or we press reset. On the other hand, if the temperature was not above that threshold, no flame, we're just going to go back to our while one loop and sample the temperature again. Okay. Looking at this program, after the initial setup that only happens once, we can see there are 2 possible states for our candle. The candle could be in the outer loop, where it's sampling the analog value and waiting for the flame, or it could be in the inner loop, like it is right now, where the flame is burning bright. Much like our blink sketch had a high power mode and a low power mode, we need to run power profiling for both of these modes to understand our candle's power consumption and estimated runtime. So let's take the candle burning bright first off. I'm going to show a power trace here, and it's kind of a bit all over the place. It goes up, it goes down, and that's to be expected, right? Sometimes the candle's flickering lighter, sometimes it's dimmer. We're seeing a current draw in this case of 5.24 milliamperes. That means, plugging the numbers into our equation, we can expect this battery to last about 7 hours with the candle glowing, which is not a long time, but hey, it's a small battery. Give it a break. Now let's try the case of the candle being dark, waiting to be lit. In this state, we see a pretty steady current draw, this time 2.45 milliamperes. This is telling us that even when the candle isn't lit, it's just waiting around for me to strike a match, we're still pulling milliamperes of power. And remember, 2.45 milliamperes is 2,450 microamperes. This is bad news. Plugging the numbers into our equation, we can discover that without even lighting the candle once, the battery will be drained in less than a day. This does not spark joy. The problem here is we're using the CPU, the thinky part of our gadget, to do our sensing. Like, take this graph of the temperatures that the candle experienced just now when I lit it. When the program started, we were taking a measurement. Then we did it again, and again, and again, and again. We keep running this measurement until the temperature rises and we know to turn the candle on. The problem here is the CPU is awake the whole time. We're wasting a ton of energy just waiting for the one moment that matters. What I'd really like to do is have the CPU sleep through all of this waiting and then only wake up when the flame hits the sensor and it's time to wake up the candle. What we really want to do is something like we did with our blink sketch, except we don't want to sleep for a period of time because we don't know when someone's going to light the candle. Could happen in 1,000 milliseconds, could happen in 10,000, could happen in 1,000,000. We don't want to sleep for a period of time. We want to sleep until something happens. What do? Well, here's the thing. The watchdog timer that Sleepy Dog used, that's only one of many things that can wake us up. If we want to wake up at a certain time of day, we have a real-time clock for that. If we want to wake on a button press, we have an external interrupt controller. We can wake on a touch input, or we can wake on the comparison of an analog value. So this analog comparator is a piece of silicon that's inside of our chip already. And we can basically configure it where our temperature sensor's on one pin, and we have a reference voltage on the other. And the analog comparator can compare those two continuously without any CPU involvement. So yeah, basically we can have it look like this. We have a reference voltage here, our temperature on the other, and we can keep the CPU entirely asleep until the temperature rises and we know to turn the candle on. So let us revise our candle code. This next slide is going to be a little more complicated with the peripheral setup. Try not to worry about that. I'm going to highlight the important part. After we do all of this setup for our analog comparator, we have this important line. We set up an interrupt where we can wake up when the threshold is crossed, and then we enter sleep mode by calling this WFI instruction, wait for interrupt. At this point, the CPU will go to sleep at this line of code, and it will not wake up until the interrupt happens, and we wake up, yeah. Once we wake up here, the code will resume, the candle will turn on, and we'll be able to burn the flame. Okay, so now we have this revised code that puts us into sleep mode instead of sampling repeatedly. How are we doing now? Well, in this new mode, we're consuming 433 microamperes, which is a marked improvement, right? That's like an 82% reduction in current draw. Now, the candle's going to last 3.5 days waiting to be lit, which is a lot more than a few hours. Still, we were promised single-digit microamperes in this data sheet. Why aren't we seeing these low numbers that we were promised? That brings us to lesson 2. Every little bit counts. Because it turns out the CPU isn't the only thing we have to worry about. Okay, So on the left, our data sheet promised in low power standby mode, we could expect to consume 2.2 microamperes. But in that low power mode, that's not the only thing running. We also started running the analog comparator, and elsewhere in the data sheet, we can find the analog comparator consumes another 23 microamperes. So that's on us. We just didn't consider that. Fine. Still, adding these up, we're still off by an order of magnitude. Like, 2 plus 23 is not 433. This is known. So we got to investigate a little further. It's at this point in the class that I put the schematic back up and asked for opinions on where people thought that the extra power consumption might be coming from. And hand shoots up, and they're like, yeah, it's your sensors right there, right? Because these circuits do sense my temperature and light, but they're also resistors between power and ground, which makes this an Ohm's law thing. Like, up here, that is a 10,000 ohm resistor in series with a 10,000 ohm thermistor, which means we just made a 20 kilo ohm resistor between power and ground. If we divide our 3 volts by 20,000 ohms, we end up with 150 microamperes of current flowing. And then we did it all again with the light sensor. What's even worse with the light sensor is the resistance of the light sensor goes down as it gets brighter. So if the candle were in a bright room like this, the photoresistor's value might be 2,000 ohms, which means that we've got more current flowing, 250 microamperes. And again, this current is always flowing through these things because these are just dumb resistors between power and ground. The CPU being asleep doesn't matter here. So if we add up our current budget, we think the microcontroller is pulling 25 microamperes, the temperature sensor is pulling 150, and the light sensor is pulling 250. That adds up to an estimated power consumption of 425 microamperes, which is pretty freaking close to the number we're actually seeing. So how do we fix this? Well, the obvious one here is we can get rid of the photoresistor. Like, we aren't even using it in our code. We can light the candle with just the temperature rise. So right now, all this is a battery slowly drainer. As far as the temperature sensor, we got a couple options. One option is to add an additional pin that can enable or disable the circuit. So in this example, I've added a second pin called TS enable. And this is what we do in SensorWatch. When we want to take a temperature reading, we enable the temp sense pin, we pull it low, and that allows power to flow through this circuit. Then when we're done sensing the temperature, we turn TS enable off, and that cuts off the current flow. Another option is to increase the value of the resistors, say a 510K resistor and a thermistor. And yeah, this will cut your power consumption down by a lot, because now, Ohm's law, we've got a mega ohm between power and ground. I will say, this can have some implications for using an analog to digital converter when you care about the actual value. But without getting too far in the weeds, I will say this will work great for our analog comparator circuit. So on the second of 3 purple Osh Park boards, I have soldered in a new 510K resistor and a 510K thermistor. What does our power trace look like now? Answer, 50 microamperes. You can barely see it at the bottom here because I didn't change the scale. I wanted to compare. When we used the CPU for our sensing, we were burning thousands of microamperes. Sleep mode cut that down by a lot, more than 80%. But our poor choice of components still left savings on the table. By making wiser choices and fine-tuning our circuit, we cut sleep mode power consumption by 98%. What does this look like for battery life? Well, answer, instead of 3.5 days in standby, we can now go more than 30 days waiting for the candle to be lit. And I gotta say, for a project that intentionally made bad choices just to make a point, I'm not displeased with this outcome. Still, this doesn't affect our wake mode all that much. Before, we got 7 hours, 3 minutes of light. After, we get 7 hours, 38. That's because the LED's power draw is rather, yeah, it's large. I mean, there's no way around it, right? The LED is taking electrical energy and turning it into light energy, and that's just, yeah, it's gonna burn power. This brings us to the next lesson. Get down with low power tech. So yeah, an LED, not likely to be the lowest power thing. Still, not all technologies have this property of turning electrical energy into some other kind of energy. Like an LCD display, like the one in SensorWatch, it displays things by blocking light instead of generating it. So yeah, lighting up these segments doesn't actually consume that much power. Compare this to an OLED, which, yeah, can be 1,000 times more power hungry, on the order of milliamperes. And that's because it's doing the same thing as our LED right here. It's taking electrical energy and turning it into light, the OLED display. So to drive this point home, I profiled a few different pieces of display tech for this talk, using a simple application, a clock. I made a few clocks. So take this OLED screen from Adafruit. Looks great, and it displays the time. But a quick glance at the power profile, and we see that it's drawing 15.2 milliamperes. And this is with the CPU turned off. 15,000 microamperes makes this unlikely to work in a coin cell, low power kind of project. Next, I profiled the oddly specific LCD. This is a board of my own design. And in this case, we pull 111 microamperes, which is respectable. We're going to do better in just a sec, but pretty good start. Also, I profiled this e-paper display, and people love e-paper. I love e-paper, personally. It's stable. You can write things to it, and even without any power, it retains its state. Alas, when I measured the quiescent current draw here, I saw 620 microamperes. That's not the challenging part, though. The challenging part is it takes a lot of energy to update the display. This was a red, white, and black display, so it took 15 seconds to update. And during that time, it's generating the boosted voltages necessary to drive e-paper. So yeah, over the course of a minute, we were pulling 4.6 milliamperes. Yeah. E-paper can be great for things that don't change that often, or if you can optimize it, but it's, yeah, probably going to need to be rechargeable at this point. Now, I will say, this example is a little bit unfair to the e-paper, because some displays have a faster refresh cycle, so you can shorten the time you spend up here. And if you can cut power to the e-paper display driver chip, you can also lower the quiescent current draw down here. But that's actually a good time for a quick side note on turning things off can be another great way to save power. Like, if you have a MOSFET power switch or a second regulator that can cut power to the e-paper display driver chip, then you can get rid of that quiescent current draw. It also works for things that are not external, but are internal to your system. So this was the temperature sensing code right here. Watch this fly in from the top and bottom. We can also enable the ADC when we want to take a reading and disable it afterwards. Because remember, the ADC also consumed power, 23 microamperes. So by disabling the ADC, we can save that current. Similar story with the candle and the analog comparator we're running here. We set up this whole peripheral up here to do our comparison. But once it's done its job and woken us up, we actually never need it anymore. We can add a line of code here to disable the comparator and save that 23 microamperes. Because it's going to keep on running and doing its comparison even though we're never going to check it again. It doesn't know that. We need to tell it so. Point here is there's a lot of little optimizations all over the place here. You just need to adopt that low-power mindset to find them. I will also say, I've shown some Arduino code today, but I suggest you might not want to use Arduino here. It turns on a lot of peripherals and functions and stuff right at the outset before you even get to call your setup function, and it makes those choices that might not be the choices you want to make when you're optimizing for low power. I will say for the last few years, I've been working on this low-power framework called Gossamer. It's designed for the SAMD and SAML chips, like the one in the candle and the one in my watch. The premise of it is that it's sleep-forward. So this is its main loop on the right here, and you still write your setup and loop functions like Arduino, but if your loop function returns true, then Gossamer knows that it can put the CPU to sleep and enter standby mode. So yeah, this is designed basically for you to set up wake things at the top and then enter standby mode most of the time, so your application sips microamperes by default. I'll also mention, I actually first shared this publicly 2 years ago at Teardown 2023. Back then it was very early days, and now it is running the code on every sensor watch that ships. So we're there. But I digress. Okay. For this next section, we're going to build a clock, and we're going to do it using the LCD we saw just a second ago. We're going to do it in a power-optimized way. But before we talk about building the clock, I do need to mention, these are two custom circuit boards you're looking at. and they're circuit boards I designed and optimized for low power. That's the next lesson. Optimize the hardware. So let's take a look at that green circuit board from up top. I call this one Feather Low Energy, and it's one of my designs that makes its way into a lot of side projects. It probably looks pretty familiar. It's similar in a lot of ways to the Feather M0 that we used in our Blink example, but the Feather Low Energy is optimized for low power applications. For one thing, it uses a different chip, the SAM-L21, that's designed to run in the realm of single-digit microamperes. We'll talk about that in a second. But right now, I want to talk about something simpler. How do we get power to our board? So we have a USB port on the left over here, of course, and we have this JST connector that accepts a battery, a LiPo. But those voltage sources are 4 and 5 volts, and we need 3.3 volts to run our microcontroller. One of the simplest ways to get 3.3 volts, especially if your input voltage is not that much higher than the output you need, is to use a low dropout regulator, an LDO. Pros of this, it's very simple. You don't need a lot of external components, just 2 capacitors. And if you're driving low current loads, it can actually be reasonably efficient. In fact, if you go to Adafruit's Feather specification page, they have a recommendation here. They suggest the AP2112K regulator. Now, before we do this next thing, I like this part. I've used it in a ton of things. In fact, for the sake of this talk, I soldered together a Feather Low Energy with this AP2112K regulator. Then I loaded up some code that just did nothing but put the microcontroller straight to sleep. When I profiled it, I saw 63 microamperes of current draw, which I'm not wild about. Like, my microcontroller says it can do single digits. I was hoping for a lot less than that. What gives? Well, you can go to the datasheet for the 2112K and scroll down to its features, and it says low quiescent current draw of 55 microamperes. As you can imagine at this point in the talk, I'm reading this like, low? Double digits? Really? Instead, let's talk about the regulator I actually put into Feather Low Energy, this part, the XC6220. It promises just 8 microamperes in its power-saving mode and 50 microamperes in its normal mode. This 2-mode thing is actually kind of cool. Basically, when my gadget is drawing less than a milliamp of current, it enters in this power-saving mode, and it stays there until we need to pull more than 10 milliamps, which is really great for the Feather Low Energy, because if we're smart with sleep modes, we can probably spend most of our time down there. When I profiled a board using this regulator with my chip in sleep mode, I saw what I was hoping to see, quiescent current draw in the single digits. Now that is what I call low power. Okay, so before we move to the next board in our design, I want to say I'm not dragging Adafruit for recommending this part. Like, engineering is all about trade-offs. Sometimes you make a choice in one place, it has an effect in another, and there's a lot of factors to take into account when selecting a component. In this case, though, you do pay for it with money. The AP2112K costs 15 cents on Mauser, or 8 cents at quantity. The XC6220 costs 95 cents, or 38 cents at quantity. So yeah, for a personal project, that's 80 extra cents, or 30 extra cents if you're buying a reel to put it into a product. Still, if you attended my accounting talk last year, you probably have it in your head that 30 cents on the BOM probably leads to 80 cents at retail. So yeah. Point here is, though, depending on your priorities for a gadget, this might be worth it. Okay. So with Feather Low Energy in place, let's talk about the other board, the LCD Feather Wing. We mentioned a second ago that LCD tech is pretty low power, and the LCD Feather Wing drives that low power display with a low power chip, an I2C LCD driver. This means we have to talk to the display driver over I2C. In the datasheet here, we can see the LCD controller has some display memory, and we have to write to that display memory over the I2C bus. The good news here, though, is once we've written data to the display memory, the LCD driver chip will just keep driving that onto the display. We don't have to talk to it anymore. So here's our code. Let's assume we have a function called display time that knows how to talk to our LCD. Let's say that we've configured our app loop to wake up once every 60 seconds to update the time on the clock. When we code the clock this way, we're doing pretty good. For the most part, we're sitting way down at the bottom of our graph, but there is a spike of about 3 milliamperes when we update the display. So for this next slide, I'm going to zoom way, way, way in on that spike. This graph shows 25 milliseconds in the life of our gadget, and you can see the spike lasts 13.5 milliseconds. In that time, the CPU wakes up, we do some communication, and then it goes back to sleep, and we settle back down at this low power mode, right? The good news is, since this spike is so short, and it only happens once a minute, our current draw averages out over the course of a minute to just 14.3 microamperes. But, oh no, feature creep. Let's say we want to do more. Let's say we want to blink the colon. Tick-tock, on for a half second, off for a half second. So to implement this feature, let's say that display time knows how to blink the colon. We're just going to now start calling it a lot more often. We've configured our app loop to wait every 500 milliseconds instead of every 60 seconds. Our power trace looks a lot spikier now. This is, again, 1 minute in the life of our gadget, and we can see where it's averaging 29 microamperes, which is more than double the current we were drawing, updating the screen once a minute. Doubling the current consumption is going to cut our runtime in half. This is also known. But here's the thing. I'm looking at this display right now, and I'm thinking, most of it's not changing. The only thing changing is the colon. Looking at the display memory here, I'm thinking, what if I could update only the bits that are changing and not bother pushing extra data out over the bus? It turns out this chip has the ability to accept partial writes to display memory. So if I write just 1 byte, the first byte, and that byte contains the colon, I can update without having to push all that data over the bus. So let's add a function that only pushes 1 byte to the display, blink colon. 1 time out of 120, the time will have changed, and we'll have to call this display time function that updates everything. But the other 119 times, we can call this new function that only pushes 1 byte. Could this possibly have an impact on our power budget? Well, first I'll show this. The left is the old spike for when we updated the entire display. And on the right is the new spike. You can see the spike on the left lasted nearly 14 milliseconds, and it spent a decent amount of that time hovering near 1 milliamp. Whereas on the right, the spike only lasts 5.7 milliseconds, and it doesn't have nearly the power impact. The line stays way down there. All told, when we trace this new version of blinking over the course of a minute, we get average current consumption of just 18 microamperes, which, to be fair, is 4 more than we previously had with updating once a minute. But it's a lot less than the double that we had when we were naively updating the entire display every time. This is another way of optimizing the high power parts of your sketch. Like, you can, instead of bringing the high part down, you can narrow the amount of time that you spend there. So we couldn't do this with our blink example without like shortening the blinks, which was kind of the point of our sketch. But in the case of the LCD, no one cares how long we spend updating our display. The colon blinks either way. So we were able to bring our current consumption from 28 microamperes down to 18 with no impact to the user experience. I will also point out at this point, there is no inevitability to any of this. You have to think about it when you design the hardware. So I'm going to show, this is the segment mapping for our display. Just because of the way it's laid out, the indicators have to be at the far left and far right of the thing. And so the signal lines that drive them are at the far left and far right. But I wanted to update those in 1 byte, the first byte in display memory. So when I actually routed my circuit board, you can see this kind of goofy trace that kind of jumps over to the right. I needed the first 8 bits in display memory to address the 2 segment lines on opposite ends of the display. So yeah, the only reason we get to have that short spike and that 1 byte update of the colon is because of this one goofy trace. Similarly, on the SensorWatch custom LCD, which I think is shipping now at Crowd Supply, I wanted to be able to blink some of my indicators, including the colon, in a low-power way. But my microcontroller datasheet told me I could only do that if they were connected to these 2 pins. So when I drew this drawing for my manufacturer, I colored them blue, and I put a note at the bottom saying the blue elements have to be addressed on pin 25 or 26, which are where that corresponds for my gadget. Lo and behold, when they came back with their engineering drawing, they routed those segments on the pin that I requested, and that's why you can blink the colon on the custom LCD in a low-power way. This brings me to the last lesson, and it's maybe the subtlest one. Learn to think through your problems in a low-power way. A lot of times there are many ways to get to an answer to a question, and if you focus on figuring out which one is the low-power way to do it, that's going to help. For this last lesson, I am going to talk about Sensor Watch and the new accelerometer sensor add-on that we're shipping with it. It looks like this. It's very simple. We have the accelerometer, 2 decoupling caps, and then test points for power, ground, and a UART if you want it. So this is my setup for the very roughest power profiling of Sensor Watch. I've soldered these 2 very fine enamel wires to those test points on the accelerometer board, and I am kind of back powering the board through the 9-pin connector with 3 volts. So on the left here is a power trace of Sensor Watch with the accelerometer sensor powered down, so no accelerometer. And on the right, with the accelerometer sensor powered up. It's sampling acceleration at 1.6 hertz. So 1 or 2 times a second, it's going to sample the acceleration and, yeah, no. And you can see those little spikes here. Those little spikes at the bottom, that's the accelerometer sampling the acceleration value. So compared to the accelerometer off state, which is 10.5 microamperes, the accelerometer on state averages 10.99, 11. Glancing at the datasheet for this accelerometer, that sounds about right. Sampling at 1.6 hertz, depending on the mode, I should expect to see about a half a microampere of current consumption. My goal with the accelerometer is to sense that acceleration value and see when it crosses over a certain threshold. When it crosses that threshold, I can be like, it looks like you might be going for a run, and I can track the wearer's workouts. The problem with this, though, is I plotted this graph by reading the acceleration values over the I2C bus. And as we just saw, talking over the I2C bus takes power, right? So here's that power trace from a second ago, 10.99 microamperes. In this situation, the accelerometer has sensed the data, but we haven't actually read it out. If we modify the code to actually get our data, we're seeing a lot more current draw, over 18 microamperes. And again, this is not because the accelerometer on the left is any more power hungry. It's because we're waking up the CPU to to read the data. To give you an example of the real-world implications of this, napkin math suggests that at 11 microamperes, I can get away with running Sensor Watch for 54 weeks on a coin cell. Whereas at 18.2 microamperes, that's cut down to under 33 weeks. And the problem here is I promised on my campaign page over a year on a single coin cell. Implementing this activity tracking this way would make a liar out of me, and I don't like that. But this leads to a problem. How am I supposed to do activity tracking if I'm not allowed to talk to my sensor? Well, the answer is we can do something similar to what we did with the candle here. Just like we could configure our microcontroller to wake up when there was a voltage crossing a threshold, we can configure our accelerometer to wake up when motion crosses a threshold. So I very intentionally picked apart an accelerometer part that is capable of determining whether it's stationary or in motion, all inside the accelerometer. So when the wearer's motion goes below a certain threshold, and it stays there for a little while, the accelerometer can assert a logic high signal saying the wearer is inactive. When it goes back above that threshold, the accelerometer can then assert that line low, and we know that the user is active. We've broken out those signals from the accelerometer and routed them to Sensor Watch over the little modular 9-pin sensor connector. And as a result, we now have just a GPIO pin that we can read, and that will tell us whether the wearer is active or inactive. So now determining whether the watch is moving or not doesn't require I2C at all. We just read a GPIO line, and if it's high, the watch is stationary, and if it's low, the watch is active. In fact, once we've set up the accelerometer this way, we barely need to talk to it again, which is great
because the I2C bus consumes power, whereas just reading the state of a GPIO pin takes next to nothing. So this is the kind of low power mindset that I hope you take away from this talk. And as a side note, I will add, I am not done figuring this out yet. Sleep tracking is next. There's a way for this accelerometer to also assert a signal line when the wearer's your wrist flops around and orientation change. I don't have a slide for this, but I configured a timer counter to count up the number of orientation changes per minute, and I can see your wrist flops around a lot more during the day than it does when you're asleep at night. Problem was, configuring it that way cost 30 microamperes, so I couldn't do it. But I have some ideas, and yeah, I'm thinking through the low power way of doing it, and I know we're gonna get there. So yeah, very quickly recap, and then I can take a couple of questions. Yeah, we talked about brain, go away, the importance of putting the thinky parts of your gadget to sleep. Every little bit counts, looking at every component on your board and every element of your design that you choose to energize or de-energize. Getting down with low power tech, picking stuff at the outset that lends itself to low power consumption. That can be hardware like an LCD, that can be software like a framework that you use. Optimizing the hardware, picking parts that make sense for your use case, and planning ahead to design for low power. And yeah, learning to think through the problems in a low power way. If there's many ways to an answer, see if one can lead you there by burning less power. And yeah, that's all I got for you, so thank you so much.